I want to welcome you again to Math 1350. In this lesson, we're going to begin our semester by determining probabilities. Please remember to read your textbook, page 468 to 479. We'll cover this. The homework is on my math lab. That'll be posted on my math lab. If you ever want additional practice, the textbook also has a lot more problems that you can go to and practice. Before we get started, I'm just going to pull up my math lab real quick and show you what that homework will look like. So if you go to your homework, you can come here to homework or you can go to course home. Ignore the dates. This isn't going to apply to this semester. But if you click on homework 9.1, you can see here's the homework set for this first lesson. The homework is unlimited tries, and so you can retry those problems again and again until you get them correct. I encourage you when you're doing your homework, you can either print the problems and write your work there, or I would keep a spiral and show all your steps, show all your work. That way when you are taking your quizzes and your exams, you have something to reference back to. So definitely write down your work and your steps as you're doing your homework. As you come to a homework problem, remember when using my math lab, there's always question help. And so the reality is we are trying to cover K through 8 math, and it's impossible for me to do one of every type of example. That's why on my math lab, if you come to a problem and you're not sure about it, you can come up here to question help and view an example like the problem that's in the homework, and it'll take it through step by step for you. Okay, going back to the notes, we start chapter 9 by discussing probabilities, and this is something that your students really do enjoy. A lot of probability was moved to 7th grade, and so several years back a lot of the TEKS changed and a lot of stuff was moved down. So there was 7th grade geometry that was moved to 4th grade. A lot of the TEKS were moved down a grade level or so. Probability is actually one of those things that was moved more upward towards 7th grade. And so if you study the 7th grade TEKS, you're going to see a big section there on probability. First definition we have here is an experiment. An experiment is an activity whose result can be observed and recorded. For example, drawing a single card from a standard deck. Other examples would be rolling a dice, spinning a spinner, drawing a piece of candy out of a jar. There's a lot of different experiments you can do in your class. I will tell you, if you have questions on your exams or on your homework about a standard deck of cards, that's probably something you need to go over more because students these days do not play card games as much and they're not as familiar with the cards. An outcome is the possible results of the experiment. So for example, drawing the 2 of clubs is one outcome. Drawing a king is an outcome. If you're rolling a dice, rolling a 3 would be an outcome. It's a result that you can get when you conduct an experiment. Third definition is the sample space. The sample space is a set, so we do use set notation, and it's where you list all of the possible outcomes for the experiment. So here we have 52 outcomes because I listed every possible card you could draw in a standard deck of cards. If we did have a dice and we were rolling a dice, the sample space would be S equals 1, 2, 3, 4, 5, 6, because those are all of the possible outcomes you could get on a dice. If you are flipping a coin, your sample space would be S equals H, T, because flipping a coin is either going to result in heads or tails. Fourth definition is event. Event is a subset of the sample space. And so, for example, it's being specific, what kind of event you want to happen. Event A, I want to know all of the outcomes that would include drawing an ace. Well, in the standard deck of cards, there are 4 aces out of the 52 cards, so my event would be ace of hearts, ace of diamonds, ace of clubs, ace of spades. If you wanted to draw a queen, it would be the same thing. Queen of hearts, queen of diamonds, queen of clubs, queen of spades. That's a specific event. It is a subset of the sample space. All right, we're going to go through and we're just going to discuss the cards as well, how many cards there are, how many suits there are, etc. So number one, it says use a standard deck of playing cards to answer the following questions. First question is how many cards are in the deck? If you were teaching this in your class, I would bring in several decks of cards, pass them out, and let your students familiarize themselves with it. So we know that there are 52 cards in the deck. Those 52 cards are split into 4 suits. So that is number 2. How many suits are in the deck? That would be 4. Name them. That's going to be spades, clubs, diamonds, and hearts. And it says what color is each suit, and so I'm going to label these 2 suits are going to be red, whereas these 2 suits here will be black. Number 3, how many cards are in each suit? Well, it should make sense if there's 52 cards in the deck and we divide it into 4 suits. 52 divided by 4 would give me 13 cards in each suit. Now we're going to name them, and so if we name them, we have a 2, a 3, 4, 5, 6, 7, 8, 9, 10. Then we have a jack, a queen, a king, and an ace of each suit. So for example, we have a 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, etc. We have a 2 of spades, 3 of spades, 4 of spades, 5 of spades, etc. Number 4, how many face cards are in the deck? Name them. These cards right here are the cards that have faces on them. So we have a jack, queen, and king, but we have one of those of each suit. So there's 3 of them times 4 suits. That's going to give me 12 face cards. If we name them, I have a jack of spades, I have a jack of clubs, I have a jack of diamonds, and I have a jack of hearts. I have a queen of spades, a queen of clubs, a queen of diamonds, and a queen of hearts. Finally, I have a king of spades, a king of clubs, a king of diamonds, and a king of hearts, and that is my 12 face cards in the deck. So that just kind of goes through the deck of cards, naming the different suits, naming the different kinds of cards that we have. Now we're going to actually start writing some sample spaces. So number 1 says write a sample space for each experiment. How many outcomes are in each sample space? So on number 1, we're going to toss a fair coin once. When we write these sample spaces, we make sure that we write and use proper notation. So the way that we write a sample is we use a capital letter equals, we use braces, and then we write the outcomes with a comma in between. So all of the possible results that you can get by flipping a coin is heads or tails, so that would be the sample space. This particular experiment has 2 outcomes. All right, going to the next page in your notes, we're going to continue the same thing. We are going to write the sample space and then the number of outcomes. So now let's take a coin, but let's toss it twice. So when we toss it twice, that's definitely going to make a difference. My sample space now is I could get heads for both of the coins. And let me erase that and make that look a little bit better. So when I toss the coin, I could get heads for both of them. I could get tails for both of them. I could get heads first, tails second, or tails first, heads second, and that is 2 different outcomes. So for this experiment, we have 4 outcomes. On the next one, we are rolling a fair die, so we have 1 die. So the sample space, what I could get, the outcomes would be a 1, a 2, a 3, a 4, a 5, or a 6. So here, 6 outcomes. Okay, next definition we have is experimental probability. I kind of like to discuss experimental and theoretical together, and so we're going to kind of approach 5 and 6 at the same time. Experimental probability is the probability that's determined by actually doing an experiment. So for example, we might flip a coin 100 times. And if we flip it 100 times and we get 47 heads and 53 tails, that adds up to 100. The probability of heads would be 47 out of 100 because that's what happened in the experiment. Theoretical is when you don't actually do the experiment, it's what would happen under ideal conditions. So theoretically, if you flip a coin 100 times, the probability of getting heads should be 50 out of 100, which is 1/2. And so experimental and theoretical probabilities can be the same, but they're not always going to be the same because experimental is determined by what happens. So number 5 says the probability determined by observing outcomes of experiments. Probability of A is the number of times A occurs over the number of times that the experiment is performed. And so the first example is find the experiment of drawing an ace when 13 cards are drawn. If I was doing this in a face-to-face class, I would bring in a deck of cards, and when I bring in the deck of cards, I would have one student draw 13 cards, and we would see out of those 13 cards how many aces that we have. So I actually have a deck of cards here. I'm going to draw 13 cards, and I'm going to write down what I get, and then we will, from what I get, determine the probability of getting an ace when I draw 13 cards. All right, so here I go. The first card that I get is a 2 of clubs. Next thing is a king of spades. Next card is a 3 of diamonds. Next card is an ace of diamonds. Next card is a jack of diamonds. Next card is a 4 of clubs. Next card is a 10 of clubs. Next card is a 10 of diamonds. Next card is a 4 of spades. Next card is a 5 of spades. Next card is an ace of spades. Next card is a queen of diamonds. And then my final card is a 5 of clubs. So when I look at this, here are my 13 cards. I actually drew them from a deck. And so from that data, from that experiment, from those outcomes, I can now write the experimental probability, because I did an experiment, of drawing an ace. The way that you write this answer, you need to be proper. The experimental probability of drawing an ace, the experimental probability of getting an ace is equal to, well, when I look at my data here, I have 2 aces out of 13 draws. That does not reduce, so my answer would be 2/13. Another one is we are going to flip a coin 10 times. Again, if I was in a face-to-face class, I would actually have a student come up and flip a coin 10 times. So what I'm going to do is I have a generator opened, and so I'm going to have it generate and just flip that. And while we're doing that, I want to show you, you can go online and easily find things that generate for you. So let me go online and see. Here is a dice generator. If I want to do a coin flip generator, I'm just going to type in an interactive coin flip, coin toss. And there's going to be different ones that show up. So we'll see if this works. Some of them you have to have different versions of Flash, etc. And so if you didn't want to have a student come up, you could just have them or pull this up online and do it. So what we're going to do is we're going to toss it. This one says 10 times. So we'll toss. And here are the results that I have. And so that's definitely something you could do. That example said find the experimental probability of getting heads. So on this I count 1, 2, 3, 4, 5, 6. So I'll have 6 out of 10. So the probability here of getting heads is equal to 6 out of 10. I reduce that to be 3/5. So when we go online, there's a lot of different generators that we can look at. Now, in reality, what we think should happen does not always happen. Theoretically, there are 4 aces in the deck. And so theoretically, you should get 4 out of 52 or 1 out of 13 aces. That's theoretically. Heads, if you're flipping a coin, you should get heads half the time theoretically, but we can't control the experiment. So we didn't get heads half the time, we got heads 3/5 of the time. Next thing we have here is the law of large numbers. What this says is, and this is a theorem that was developed by Bernoulli, which is a mathematician, as the number of trials of an experiment increases, the experimental probability will approach a fixed number, which is the theoretical probability. What that means is the more time that you do an experiment, that experimental probability will get closer and closer and closer to a theoretical. So when I tossed the coin 10 times, I got 6 out of 10 heads. If I keep tossing, keep tossing, keep tossing more and more and more times, that will get closer and closer and closer to a half, because you should get heads half of the time. All right, theoretical probability is the probability that is assigned under ideal conditions. So it's what we think should happen. For an experiment with sample space S and equally likely outcomes, the probability of event A is P of A is the number of elements of A over the number of elements in the sample space. So how many times or how many outcomes that the event can happen over the entire sample space. So for example, find the theoretical probability of drawing an ace in a standard deck. Well, we know in a standard deck the probability of getting an ace, and please use the correct notation, is 4 aces out of 52 total cards, and that reduces to 1/13. You should get an ace 1/13 of the time, but we can see from above that's not necessarily going to happen when you conduct the experiment. All right, the bottom of the page, we're going to do some more examples. A fair spinner numbered 1 through 9 is spun. Find the probability. That's something you could probably find online as well. You could also go online, and here I just found one that you could print out, hand to your students, and have them make, and they could look at that. They could actually do an experiment with that. Here we're going to think about it theoretically. So if I have the numbers 1 through 9, I want to know if I spin it, what's the probability I get a multiple of 3? Well, if I pull that spinner back up and I look at which numbers are the multiples of 3, that would be 3, 6, and 9. Those are multiples of 3. So the probability of getting a multiple is 3. There are 3 of those outcomes out of 9 total outcomes, and that reduces to be 1/3. Part B, what's the probability if you spin, you get a 4 or a 7? That's 2 outcomes on that spinner. So that would be probability is equal to 2 outcomes out of 9 total outcomes. Last one like that, the probability of getting a composite number. Remember, in our number system we have prime and composite numbers. The number 1 is neither prime or composite. 2 is prime, 3 is prime. 4 is composite, so I'll write that down. 4 would be a composite number. 5 is prime. 6 would be composite. 7 is prime, but 8 and 9 are both composite. And by composite, that means that they are divisible by a number other than 1 in themselves. And so composite numbers on that spinner is 4 outcomes out of 9 outcomes. Okay, going to the next page in your notes. We have some terminology. At least 1 means 1 or more. At most 1 means none or 1. Your students, you're going to see these in your problems. Definitely more of those in junior high. They really struggle with that. And so I really try to show some real life examples of that. If I need at least 1, or if I say, let's change it, I need at least 3 of you to help me, that's 3 or more. If I say, hey, I can only feed at most 5 of you, that means 5 or less. And so they have to really understand that terminology of at least and at most. So we're going to apply that to our next example. Number 2, suppose a fair coin is tossed twice. Find the probability for each of the following. Now we already wrote this sample space, but I think it's very helpful to write it again. So if I toss 2 coins, what I can get is heads, heads, tails, tails, heads first, tails second, tails first, heads second. And so I have 4 different outcomes. Part A, what is the probability that I get exactly 1 tail? So to write this properly, we would write the probability of exactly 1 tail is equal to, well, this outcome has exactly 1 tail, and so does this one. So exactly 1 tail happens 2 times out of the 4 outcomes, which reduces to half of the time. That changes on part B. I want the probability of at least 1 tail. So at least means 1 or more. At least 1 is 1 or more. So again, this is going to be 1, this is going to be 1. At least 1 tail is 1 or more, so that tails, tails works. So that is 3 outcomes out of the 4 outcomes. And these are theoretical. We're not actually tossing the coins. It's what should happen under ideal situation. Part C, at most 1 tail. So the probability of at most 1 tail means 0 or 1. So at most 1 tail, let me underline in a different color. This has 0 tails, so that would work. This would not work, so that's not 0 or 1. This would work, and this would work. So at most 1 tail happens again 3 out of the 4 outcomes. Next thing we have is some definitions. If an event has no possibility of happening, the probability is 0. So for example, the probability of rolling a 7 on a die is 0 because there's no possible way for that to happen. Next definition, certain event. If an event is for sure going to happen, its probability is 1. So for example, the probability of rolling a 1, 2, 3, 4, 5, or a 6 on a die is 1 because you're definitely going to get one of those outcomes. There's a lot of different anchor charts that you can create and post in your classroom. And one of those that I really like draws the probability chart, and it does it like this. If you want to add this to your notes. If something is not going to happen, its probability is 0. If something is for sure going to happen, its probability is 1. And you can change those to percents. If something's not going to happen, it has a 0% chance of happening. And if it's going to happen, it has a 100% chance of happening. What people don't understand is that 100% is the same as the whole number 1. And so if it's going to happen, its probability is 1. If something has a 50-50 chance of happening, then that probability is 1/2, which is a 50% chance. And then I would go ahead and add, the 4th and the 3/4, etc. All right, moving on to our next definition, we have mutually exclusive events. Those are events that have no elements in common. For example, rolling an odd number and rolling an even number are mutually exclusive events because their outcomes are not the same. Another example of that is rolling a coin or rolling a dice and flipping a coin. Those two experiments have totally different outcomes, no elements in common, so they are mutually exclusive. Complements, I hope you remember from 1350 when we did the sets unit. 2 events which are A and not are A, compromising the entire sample space. The event not A is written as A complement. For example, let A be the event of rolling a 1. So the probability of rolling a 1, that would be A. A is equal to 1. Not 1 would be 2, 3, 4, 5, and 6. Another thing that you could say is, if I wanted to actually do the probability of rolling a 1 is 1/6. The probability of rolling not 1 would be 5/6. So here there is one outcome out of 6 total outcomes on a dice. There are 5 that are not that outcome. Now what's going to happen is, if this is event A, then this is A complement. What you'll notice is these two probabilities, A and A complement, their probability should always add up to one whole. So 1/6 and 5/6 added together does equal 1. Next thing we have is some notation. This is notation that we also went over in 1350 when we did sets. So the empty set, we have a symbol. Intersection union, we have a symbol, and I show you and is intersection, or is union. And if two sets are mutually exclusive, then they do not have an intersection. And so just kind of give you a graphic on that. Here I'll do a Venn diagram. If this is set A and this is set B and they have nothing in common, no common outcomes, then there is not an intersection between the two. The intersection would be the empty set. Next we have some properties, and I feel like when you look at those properties, they look a lot more complicated than they actually are. One says the probability of event A has to be between 0 and 1. Well, we should know that to be true, because if something's not going to happen, its probability is 0. If something is for sure going to happen, its probability is 1. Every other answer would have to be somewhere between 0 and 1. And so every probability is going to have an answer that's between 0 and 1. Number 2, I definitely feel looks more complicated than it actually is. It says the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So take a second and look at the different notations of that, and I'm going to give you an example that you can add to your notes there that I hope will make that easier for you. So let's think about a deck of cards. Let's find the probability of, let's do the probability of drawing a diamond or a 5. So in a standard deck of cards, let's do the probability of drawing a diamond or a 5. What that's going to be is the probability of drawing the diamond plus the probability of drawing the 5 minus the probability of a diamond and a 5. So how many diamonds are in the standard deck of cards? That's one whole suit. So there are 13 diamonds out of 52. So the probability of drawing a diamond is 13 out of 52. Or I want a 5. So I'm going to draw for a 5. The probability of getting a 5 is there's 4 5s in the deck out of 52. The reason that this rule has to be applied, it has to be applied if A and B are not mutually exclusive. And so here's the problem. There is a card that's been counted twice because it's a diamond and a 5. It got counted here and it got counted here. That's why one of those has to be subtracted. So we have to subtract the one that they have in common, and that's the 5 of diamonds because it got counted here and here. So when we subtract it, we're subtracting 1 out of 52. And we'll do some more examples like that, but this just gives you an example of what all this terminology right here means. It means subtract the card or the outcome that has been put in there 2 times. So when I actually find this answer, I have 13 plus 4 is 17 minus 1, it would be 16 out of 52 cards, which of course would reduce to 4/13. All right, going to the next page in your notes, we have a few more probabilities. This next a few more properties, excuse me. This next property we've already talked about. The probability of an outcome plus the probability of its complement has to be equal to 1. And so we talked about that on a dice. If I say find the probability on a dice of rolling a 5, that's going to be 1/6. If I say find the probability of rolling not a 5, that's going to be 5/6. This is a complement, and if you add these two probabilities together, anytime you have the probability of an outcome plus the probability of its complement, no matter what the experiment is, the two answers should add up to 1. The last two make a lot of sense. If you have the probability of the empty set, that's an impossible event. The probability is 0. The probability of a certain event, number 5, is always going to be equal to 1. Note there is no special formula for A and B. There is just that special formula for A or B. So just make sure you note that and look at that as you're doing your homework. All right, we're going to finish up with some example problems. So the first one that we have here is a box contains 3 red balls, 4 blue balls, 5 green balls. Suppose one ball is drawn at random. Find the probability that the ball is red or blue. So for a lot of students, it might help them to kind of have a visual. So you might write for them, there is 3 red balls, there is 4 blue balls, and there are 5 green balls. You could actually create that, bring in a box full of those balls. First thing you need to think about is you see this word or, so you have to think about that special rule and if these events are mutually exclusive. Do they have any elements in common? So is there a ball that can be red and blue? No. So no elements in common. There's not a ball that's red and blue, so we don't have to subtract that out. So I'll show you what I mean by that. I want the probability that we get a red or a blue. Well, by that formula, that would be the probability of a red ball plus the probability of a blue ball minus the probability of a red and blue ball, which there is no such thing. That's why it showed on there. If they don't have that element in common, you don't have to subtract that out. So the probability that you get a red ball is going to be 3 of them out of 12 of them. Or the probability that you get a blue ball would be 4 of them out of 12 of them, which would make your answer 7/12. The probability that you either get red or blue is 7/12, which does not reduce. On this next one, it says the following spinner is spun 1 time. Find the probability of landing on an even number or a shaded piece. Now, for some reason, when this exported to PDF, the shaded part went away, so I'd like for you to shade in the section that has a 1 in it. And again, we see this or, so we have to be careful about that formula and making sure we're looking at to see if it is mutually exclusive or not. So what I want is I want the probability of landing on an even or a shaded, and I'm going to abbreviate. So what I need is I need the probability of an even plus the probability of a shaded minus the probability of getting an even and a shaded. So when I look at this, is there an even outcome that's also shaded? No. And so that does not have to be looked at. The probability of getting an even is 2 out of 4. The probability of getting shaded is 1/4. So the probability of getting an even or a shaded would be the summation of those, which would end as 3/4. All right, the last one for this page, before we go to the last page, is number 2. So on number 2, same thing. I need you to shade in again. So at this time, if you will shade in the 2, we can look at this example a little bit differently. All right, the following spinner is spun one time. Find the probability of landing on an even number or a shaded piece. What we have to consider now is that there is an overlap. There is an even number that is shaded. So this time, if I want the probability of getting an even or a shaded, same thing. It's the probability of the even plus the probability of the shaded minus the probability of the outcome that's even and shaded. So the probability of spinning this spinner and landing on an even number is 2 outcomes out of 4 total. Plus, the probability of landing on a shaded piece is 1 outcome out of 4. The problem is one of those outcomes, the 2 that is shaded, has been counted twice. These are not mutually exclusive. That's why that outcome has to be taken off. So the even and the shaded is going to be 1/4. When I add 2/4 plus 1/4 minus 1/4, I obviously get 2/4, which reduces to 1/2. Okay, going on to the last page, we're just going to answer some more questions about the deck of cards. So it says a card is selected from an ordinary deck of 52 cards. Find the probability of each of the following. So first one, if I randomly draw a deck or draw a card of a deck, I want to know the probability of getting a jack. So the probability of drawing a jack would be 4 out of 52 because there's 4 jacks out of a standard deck of 52. That reduces to be 1/13. The probability of not getting a jack, I see that that's the complement of that. I immediately can know that the probability of getting not a jack is going to be 12/13 because of that property. An event and its complement, the two probabilities have to add up to 1, and that should make sense. There's 4 cards that are jacks. That means there's 48 that are not jacks. So really this answer here would be 48 out of 52, but that reduces to 12/13. I didn't even have to think about that because I knew that if this was event A, this was a complement, and the two of them have to add up to 1. Next one, I want a spade or an ace. I see that or, so I know I have to pay attention to the mutually exclusive property. So the probability of getting a spade or an ace would be the probability of a spade plus the probability of an ace minus the probability of getting a spade and an ace. So if I think about the spades, there's 13 spades out of 52. Plus aces, there are 4 aces out of 52. These are not mutually exclusive because there is an ace that is also a spade. So the ace of spades got counted here as well as here. So I have to subtract that card that's a spade and an ace, which is 1 out of 52. When I add all those together, 13 and 4 is 17 minus 1 gives me 16 out of 52, but we know that reduces to be 4/13. Part D, I want the probability of a face or a 5. So same thing, probability that I get a face card or a 5. When I think about this one, these are mutually exclusive. There's not going to be a card that has a 5 and a face on it. So I don't have to think about this piece right here because there's not a 5 that's a face card. So all I have to do here is the probability of a face card, which we've already talked about. There's 12 face cards out of 52, plus the probability of getting a 5, which is 4 out of 52. I don't have to subtract anything here. So that's 16 out of 52, and that's going to also reduce to 4/13. On part E, I want not a face and not a 5. Well, I see again this complement. Not that, I see here the complement right here between these two. If Part D is the probability that you do get a 5 or a face card, and E wants the probability that you do not get that, I immediately know that this answer and Part E's answer have to add up to 1. If that's 4/13, then I immediately know that this is 9/13 because they're complements of each other. So the probability of not getting a face, and excuse this pen, it's not working very well, not a face or a 5 is equal to 9/13. All right, part F. Here I see the word and instead of the word or. The word and, remember there's not a special formula for that. So if I want a red card and a 9, well, I have to think about how many cards in the deck are red and have a 9 on them. That would be the 9 of diamonds and the 9 of hearts, because diamonds and hearts are the red cards, and there's a 9 of diamonds and a 9 of hearts. So the probability of getting a red card and a 9 would be equal to 2 out of 52, and that's obviously going to reduce to 1/26. Part G, the probability that we get a blue card. Well, there's no blue cards in the deck. That's an impossible event, so the probability is 0. Part H, the probability that you get a red or a black. Well, if you draw from a standard deck of cards, you're for sure going to get a red or a black. This here would be a certain event, so its probability is equal to 1. That is the end of Notes 9-1. You will go to my math lab to complete your homework.